So, I would like to continue. Somehow the number of students has gone down from the first part to the second part, but you can all get the information, and some of you might, or some of them might already know about evolutionary algorithms. So, since this is a course for people who not necessarily have the background in informatics, and certainly not all of, even those who are students of industrial engineering might not know about evolutionary algorithms, I should briefly introduce to you this concept of evolutionary, or of optimization using evolutionary algorithms. So what do we do with evolutionary algorithms? We have a certain problem that we would like to solve. The problem is the one, for example, filling that, like we have this, we have this, yes, we have here some area that we would like to fill with certain rectangles, for example, with certain tiles. We'd like to know how to do that. We have some collection of all kinds of tiles that we can select, and then we would like to fill that area. And for that we can have a certain solution, and the solution is a selection of components that might fit into that area. And so we can have all kinds of different solutions, and we have a population of those different solutions. Then we like to select parents. For what? For creating children, mutate children, evaluate children. So we would like to generate new solutions. We're not satisfied with the current solution, but we would like to modify the solution that maybe we can combine in a reasonable way information from two different solutions to this problem and create a new one which has better properties. So that's why we say we create and evaluate a random population. We know how well those solutions fit into that area, and then we select parents for combining the information from these different solutions, create children, mutate the children, modify some information in there, evaluate those children, and then we check whether we are satisfied with what we have got. Maybe we have looked at a sufficient number of potential solutions and say that's the amount of work we would like to invest here, or we say the quality is good enough and we just stop, or we say we would like to continue, and then we have to decide how to integrate those children into the old population, and then this turns around and it's a circular thing. So this again here is this population, the initial one. That's the selection. We select certain elements, we combine them, make this what we call recombination. So for example, here from those two elements we get a child which has exactly components from both. And if we combine those two here, we could get children having components from those two, and so on. Different possible combinations. Then we mutate, which means that all of a sudden we have new information in there, information that was not present in the old population. It's just random change of the information in there, and we evaluate the quality of those elements, of those solutions, get a ranking, and now the question is how we move those elements into the population such that this can be repeated. And so some elements will go into the new population, others from the old population will be replaced. Okay, now I'll make that a little bit more explicit. So evolutionary algorithms are a meta-heuristic, which you can, like this scheme, this method can be applied to many different situations, many different problems. And so we can solve optimization problems, although we can only approximate, we cannot give a guarantee that we get the optimum solution, but we can get improvements. So we would like to solve optimization problems with respect to one or maybe several objective functions. You can have single objective or multi-objective optimization. Multi-objective optimization would, for example, mean you have two different objectives and you would like to minimize both, but there's a trade-off. If you reduce one of them, the other one might go up, and vice versa. And so you would like to get as close to the smaller region there as possible, but if you have conflicting objectives, that might be a problem. So this can also be done very nicely with evolutionary algorithms. And the main applications for evolutionary algorithms are optimization problems where we have rather limited knowledge about the characteristics of the search space. So if we know everything about the search space, we can utilize that and have a fast and efficient way of optimizing. But if you don't know very much about that, we can only go selectively at certain areas. We see, oh, here, there's one device which has a high quality, there's one with a low quality, another one with a high quality, and things like that. But we don't know what's in the vicinity. Maybe here is even going further up, or like the topology or the topography of that search space, or the fitness landscape over that search space is not known. And so here, exact optimization usually would need much more time. And so we would like to do that with this more pragmatic approach, just try out in a systematic and randomized way. And the typical problems that we look at here are NP-hard problems, like bin packing actually is not here, but not listed, but traveling salesperson problem. You know the traveling salesperson problem where you have a number of cities which you would like to visit, and you would like to have a tour which has the shortest path, visiting all these cities without repeating or without visiting any city twice. This is the traveling salesperson problem, or the typical project scheduling problems, or other problems, many problems which are there. I will show you in a moment what it means to have an NP-hard problem. So the major idea here is to perform a systematic, randomized search with an evolutionary algorithm, of which with some other meta-heuristic. And here we are inspired by certain things that we can see in nature, as, for example, evolution, crossover, mutation, selection. Sometimes we also use some local hill climbing. So this is the background for evolutionary algorithm. And there are many different variants. There are genetic algorithm, evolution strategies, evolutionary programming, genetic programming, many different variants. And very often we just talk about evolutionary algorithm and just take one which is appropriate. So again, this view here, we have an initial population, then we would like to produce and evaluate new collections, new candidate solutions, and we do that by selecting parents, recombining, mutating, looking at the offspring, evaluating what we have there, integrate the offspring into the population, which is replacing some of the elements there. And then, if we have done that a sufficient number of times, we are satisfied. So this is the idea of survival of the fittest, which is quite well known from nature, that those who are the fittest for reproduction certainly make sure that their genetic pool is forwarded to the next generation. And so this is only those who are the fittest, who are the best in mating, they will survive, and that's the idea behind that. Another view on that, maybe I have too much views on evolutionary algorithms. So this again is potential solutions. They are evaluated. Now potential solutions can just be a sequence of numbers. For example, cities that you would like to visit, or projects that you would like to schedule. You have a list of projects. You say, I would like to plan them or to assign them starting times in a certain sequence. And I just pick them one after the other. And the sequence at which I pick those tasks is my solution. And then I decode. And the decoding means I have to look at the phenotype. Like if I say I have a certain sequence at which I pick certain tasks from a certain task pool, this will result in a certain schedule for running all these tasks. And I can measure the time it needs to actually run all these tasks that have to be carried out. So I can evaluate it, and I can notice, oh, this schedule is the best one, second best, third best. So I get some ranking, and based on that ranking, I select parents, perform a crossover, mutate, build a new population, and then decode again. So this is the circular view. And every iteration is called a generation. And the stopping criteria here at this point are, for example, maximum number of generations, or that you have not observed any improvement over a certain number of generations. And so this is just the same again, just in program notation. You have your initial population, P of t. You have your selection of parents, you have your mating pool. You make crossover, get a new set of elements. You mutate, get M double prime, and then you update the population. You have to get, you combine the original population with the M double prime of t, and then you have some update, some way how you actually get this new population P of t plus 1. Okay, this is just indicated down here in the bottom line. Now the question is how we perform all these different parts there. The initial point is, how do I have to represent my problem? So what is an individual? As I just said, it can be just a sequence at which I take certain tasks from a task pool that has to be executed, and I assign processing resources to those tasks in that sequence. Maybe I have a rule that tells me, oh, I always take the one which has the earliest termination condition. So those who are the most urgent are assigned resources the first. And then I get some resources sometime, but this is like the question is, how do I represent that? And there are many different ways of representing an individual or a solution. So it can be just binary values. That's the classical representation in genetic algorithms. Just a sequence of zeros and ones. This is just some coding of the problem. Maybe you have integer values, so let's say you have just these values, that those could be numbers of cities, and you would like to visit them in this sequence. Could be a representation. Then you have integer values. Could also have real values. In evolution strategies, that's what you take there. So there can be problems where you need real values to represent your problem or your problem setting. For a scheduling problem, you might have a certain priority rule, like earliest deadline first, and then you might have a sequence of real values, let's say sigma 1, sigma 2, and so on, and sigma n, and these sigmas are real values which are used to modify the priorities that you have in your priority rule. So you wouldn't take always the earliest deadline, but you would multiply the priorities with some real values, and then you get a different ranking of the deadlines than the ranking that you would have if you take the plain values. And so this would modify your schedules, and in this way you can try out other sequences. That would be an example of real values. But there are many other examples of that. Then the question is, do I need a string of elements? Or maybe I have a problem where it is more reasonable to have a two-dimensional array to represent my solution. Or maybe my solution has a tree structure. Maybe it is a program which I would like to generate, and then I have a tree structure, which is showing the different control lines of a program, or some arithmetic expression that is used for calculating certain values. And then it would not make sense to represent a tree as a sequence of zeros and ones. You can do that, you can code it like that, but maybe it's more natural to use a tree structure for that and then perform the genetic operators on those structures. Can also be just an arbitrary graph. And now the question is, how would you perform a crossover on graphs? You can define all these things, and then you have a problem-oriented genetic operator compared to an operator which would just make a crossover on a sequence of zeros and ones. So there are many different possibilities depending on the problem you are actually addressing. So you might have a direct representation where the genotype is almost exactly the phenotype. For example, if you have the traveling salesperson problem and you just write down the sequence of cities you have to visit, then you have a direct representation. You can immediately evaluate the cost of that path because you just have to look at the cost or the distances or the cost of going from one city to the next, and then you can evaluate it. Sometimes you have a parameter representation. As I said, maybe you have just here real values for modifying priorities, and then you still have to apply that heuristic, for example, earliest deadline first, modified by those real values in order to generate the schedule, which then can be evaluated. So then you have a mapping from the genotype to the phenotype, and that can be evaluated. So to represent a problem is not an easy task, and sometimes to choose the appropriate representation is the most important part in designing a good optimization algorithm. Because it's not always the case that the simple representation, direct representation, is the best for getting good optimization result. So it's always valid to look around at different possibilities to represent your problem, and then try out certain ways of representing that until you have found the best one. This is the first part you have to do. So the fitness certainly here is the quality with respect to the objective function. Like fitness in the biological sense is something different, but here we usually say it is the quality with respect to what we would like to achieve. And then we need selection mechanisms. We would like to get parents for the crossover. So how do we get those parents? So we have these elements here which have certain values, certain ranks. So we have here rank R1, R2, R3, and so on, or certain fitness values. So fitness proportional selection, there you wouldn't have ranks, there you would have fitnesses like F1, F2, F3. You have fitness values. And you could look at what is the fitness of a specific individual compared to all the fitnesses of all the individuals. That is summing up all the fitness values looking at the relative fitness of an individual, and this gives the probability at which I actually select that individual. So it means that you have some kind of a roulette wheel. That's why it's called sometimes roulette wheel selection. And you would like to draw a ball, and now you have selected this ball or coin falls into one sector, and the size of those sectors is proportional to the fitness of the individuals. So if you have a large sector, the probability is larger that the coin or ball will fall into that sector, and so the selection probability is depending here on the relative fitness of the individuals. And in this way you can select several different elements, and certainly it may also be that you can select the same element more than once. Yeah, because if they have a high probability of being selected, they may get selected several times, and then they have a larger chance of actually moving their genetic material into the next generation. And in this way, we have now a way of selecting parents. So this is always a randomized situation. We need a probability for that. Then there is the so-called rank-based selection. The problem with the fitness-based or the roulette wheel selection is if you have, for example, something where you have a very large sector and all the remaining elements are somewhere like that, then this one element having a very large fitness compared to the others will get selected almost exclusively. And the others have no chance of getting selected. And this may just be a local situation, just some local optimum, and maybe there's a better situation over there, some different area of the fitness landscape, but you would not get away from that. And there are other situations where you might have something where all the shares are almost looking exactly identical, almost no changes. Then you have random choice in there, random selection, which you really don't want to have. And so an alternative where you have a selection which prefers those which are better than others, but not too much, is to have rank-based selection. And it means that the best individual has the highest probability, the worst individual has probability 0, will never get selected, and all the others get a value in between. And the value is, or can be determined, this is just one possible ranking function, or not ranking function, one function for assigning selection probability depending on the rank, is assume you have n elements, you take 2 over n as the base probability, that's twice the random choice. Uniform probability would be 1 over n, minus, so this is the maximum, minus 2 times I minus n over n times n minus 1. So for the best one, having the index 1, this is exactly 2 over n. For the worst, for individual number n, it is 2 times here n minus 1 over n times n minus 1. Then this fraction there is exactly 2 times 1 over n, and so then the probability is 0 for the worst. And now if you have 10 individuals, the probabilities would get those values. If you look at this formula, like the maximum probability would be 20%, and then you have all the others. Individual number 10 would have 0%, and here that one, individual number 9, would have 2% selection probability. But here, independent of the absolute values or absolute differences between the elements. It's only based on ranking. So it is avoiding those two problems that are indicated there. And then we have more selection mechanisms. Number 3 is tournament selection. Tournament selection means you run a turn. What is a tournament? You are playing games. You're having a competition. And so what we do is we have our pool of elements. That's our population. We take 2 of those, and they compete. We compare those 2. So here we have a binary tournament, but you could also have a tournament with more elements. You just take the best one of those, or you could have, if you have a larger set, a larger sample, you could again have a randomized selection, like fitness-based selection. But here you only take a small sample, for example, 2 elements, and take the better one. And then certainly the good elements have a larger chance of being selected than the worst element or the worst elements, because those which are in the better half have a larger chance of meeting an element which is not as good as those who are in the lower half. And one can actually show that tournament selection leads to a similar probability for being selected as the rank-based selection. The advantage is that in order to select an individual, you only have to grab a sample, compare those 2, and you can select one. If you want to run roulette wheel selection or you want to run rank-based selection, you have to evaluate all the elements in the population, and then you can select. Here you only have to evaluate the sample that you are taking, and then you can evaluate those 2 and grab the better one. So you could also do that, as I said, with K individuals, and then select using some selection mechanism out of this small sample of K elements. So tournament selection actually is the one which has been shown to provide very reasonable results, like has the best performance with respect to leading to good solutions. Like, what do we have to look at? Let me just briefly write that down also. What we have to look is to what extent do we explore the landscape, the search space? To what extent do we actually look at all the possible parameter values, all the possible solutions? And to what extent do we exploit what we actually see? So exploration means we would like to actually go quite far or look at all the different areas there in our search space. And exploration and exploitation means if we are in an area in our search space here somewhere and we see some interesting areas, we would like to spend our time mostly in that area and we don't consider other areas. That would be exploitation of the location or the area where we currently are. And the different tournaments, the different selection mechanisms are different or having different properties with respect to exploration and exploitation. Then you could have uniform selection, just have equal probability, no preference, no selection pressure towards the better ones. For some situations that can also be positive, but normally, as I said, tournament selection, usually with a tournament size of 2, is something which is having quite good performance. Okay, so that's selection mechanisms. There are even more selection mechanisms than the ones that I have told you, but those are the major ones. Then the question is, how do we generate new individuals? We can do that by using, so this is recombination. We have 2 individuals, and we would like to select, or we would like to compare that. And and no, not compare, combine the information from two parents and recombine that into one or two children. And then we have mutation, where we perform a random change of a value at some position, that the value of a gene in the genotype, or we could also modify the structure of a genotype. So if you have, for example, here a tree structure, then certainly you could modify the structure by modifying some, or by mutating such a genotype. And the expectation and observation is that, or the expectation is that if you combine good solutions, you might get even better offspring. But if you would do just that, you would always go for the elitist, or for the best solutions, combine those, which is not always the best choice. Sometimes it's better to combine individuals which are not currently the best ones, but their offspring might have perfect properties. And so that's why we need a randomized approach. We need this randomization, that we select elements with some probability, but there's also some probability that individuals are selected which are not as good as the other ones. And only this allows us to look into different areas of the search space. So this is important for exploration. So how does recombination work? How does this look like? We have two parents with different genetic information, and then we would like to cross over. What does it mean? We select a cutoff point, a random point in that string, or whatever structure you have. You have that cutoff point, and then you recombine that into offspring 1 and 2. And so you have recombined the information. Now the cutoff point is completely random, and you can have one cutoff point. You could also have two cutoff points and have changing elements from the first and the second parent. And if you have a large K, you get close to uniform crossover, where you have a random combination of genetic material from parent 1 and 2. So for every position, you would decide whether you take, like randomly decide, whether you take information from parent 1 or parent 2. Normally, what we would like to take is 2-point crossover. Although in many standard, like initial explanations of evolutionary algorithms, people take 1 point and roulette wheel selection, like 1 point crossover, roulette wheel selection, but that is not the best possible choice. It's better to have tournament selection and to have 2-point crossover. Because the reason is that if you have 2-point crossover, like here, the probability that elements from the left part and the right part of the first parent end up in one individual, in one offspring, that probability is very low. Yeah, because you always take a cutoff point somewhere, and only if you would have the cutoff point there, you would have here that part and that part in the same offspring. But if you have two cutoff points or two cut points, then the probability for being, or for some areas here, of ending up in the same individual is the same for any two combinations of points that you select there in that parent. And so the 2-point crossover is just having better properties because it's treating the individual genetic information there in a more fair way than the single-point crossover. And then the mutation is just a random change applied to the chromosomes. Usually, if you say you have here, let's assume you have n elements in there, then you would take mutation probability of 1 over n. That means on the average, you would modify one gene in every or in every individual, but only one on the average. So this also has turned out to be a good value. Okay, that's mutation, recombination, and then we have to decide which elements actually go into the next population. And there we have the generational scheme. That means we have our population. We generate our offspring generation, and we generate exactly as many children as we had parents. And then this is our new population, the children, which means that everything that was in here is discarded. So if we had good solutions in the old population, maybe that they get lost and the children are all inferior. We certainly assume that the quality is going up. And in order to make sure that we don't lose good solutions, we can combine that with elitism. That means the best solution, or the best, let's say 5 solutions, or whatever you like, the best solutions, or at least the best solution, will survive to the next population. And only the others will in some way be replaced. And then there's steady state, where you don't generate as many children as you had in your old population, but you select only 2 parents, generate 1 child, and this child, or sometimes you generate 2 children, as I said, as I had in the example with the crossover, and this children, or these children, or this child replaces the worst individual in the population. Then you know that, well, since you replace the worst, then you will have this elitism effect. You still have the good individuals in there. If your individual, if your children is better than the older, the old ones, it's an improvement. You could also have a rule that, for example, you just put in the children that you have generated, and you delete the worst element or 2 elements from the new population. So I'm making sure that it will not get worse than what you had before. And then there is another scheme, a so-called mu lambda selection. You have a population of size mu. You generate lambda children, and here lambda is greater or equal than mu, and the best mu out of the lambda children from the next population. So in the extreme, maybe you have a population of size 1. You mutate, perform 10 mutations. You have 10 offspring, and then the best of those 10 mutated elements is the new population. Yeah, then you have, again, a population of size 1. You just take the best, mutate several times, take the best. Can be one type of mu lambda selection. So you generate more than mu children, take the best out of that. And then there is the mu plus selection, where you have a population of size mu. You generate lambda children, and so you have your population here, you have your children, you combine, and then you take the best mu elements out of the combined population. So there, the old parents have a chance to survive, the new children have a chance to survive into the next population if they are better than other ones in the old population. So these are standard schemes for, sometimes it's called environmental selection, or forming the next generation out of the old parents and the offspring that you have generated. And in this way, you get a new population. Now, I animated something not completely here. So the Y will appear there, or is at the right place, but it will be seen what that means in a moment. So this is all I wanted to tell you about evolutionary algorithms. So this is a standard way of generating or of optimizing solutions for a difficult problem. And usually it works rather fast, but you cannot guarantee to get the optimum because it's a randomized scheme. You just hope to get good enough, and that's the observation that we have in many, many application problems. Now I talked about, or I said that we are using evolutionary algorithms if we have to do with hard problems. The question is, what is actually a hard problem? So I have to remark or make a short remark on complexity. So we have, we usually define a certain class we call P, all problems solvable in polynomial time. So, for example, if you multiply two matrices, it takes order of n cubed time. If you, for n by n matrices, if you multiply them, it takes n to the 3 operations. Or if you sort a sequence of numbers, it takes time n log n. So this is polynomial time. It is in time order of n to the k for some k. And let me just briefly check something. Everything is fine. Okay. So that's polynomial time. Normally we say polynomial time is something which is more or less feasible, not too difficult. And then there are problems which we can solve non-deterministically in polynomial time. Now what's the difference? Take the example of getting the shortest path between many cities. And you find you just select a certain route through those cities, and now we have to go there and there. Now this probably will not be the shortest path. But if you ask, is there a path through all those cities of length less than a certain limit? Then I could try to find that, look at all the different paths that are possible, and this is an exponential number. All the different permutations of the cities would be a possible solution. It's an exponential number of different possibilities, and so to find out whether there is a path of a certain length, or if I would like to get the optimum path in a deterministic way, this simple approach would take exponential time. Now, if I have a non-deterministic algorithm, I say, okay, I just guess a certain path. And then I check whether this path has a length that is less than my constraint that I have. And I can check whether that solution is okay in polynomial time. So if I guess right, or if I guess in an optimistic way, or have luck, I can solve the problem in polynomial time. That means there is a potential guess such that I can solve the problem in polynomial time. And if there is a path of a certain length, then there is one potential guess that I could have chosen, and so it is an NP. Yeah, if there is a potential way of selecting such a path, such one permutation, and I can determine whether this potential solution actually is the one I selected. If I can evaluate that in polynomial time, that is an NP. Okay, so I guess the solution, check validity in polynomial time. And it is unknown whether those two classes are different. Like we have for every problem in NP, we can generate an algorithm which will get a solution in exponential time. because we can simulate the non-deterministic approach in exponential time with a deterministic approach. But we don't know whether maybe there are some clever methods of actually solving a problem which is solvable non-deterministically in polynomial time, also in that time with a deterministic algorithm. And so these two classes seem to be quite close together. The only difference is whether it is deterministic or non-deterministic. And as I said, the standard deterministic methods for solving a hard NP problem need exponential time. And now the question is, what is actually an NP-hard problem? So this should be a problem which is very difficult. And we characterize such a problem by saying that this problem, or that every problem y out of NP, should be P reducible to X. What does it mean? P stands for polynomial time reducible. If a problem or a problem y, any kind, the pen has a very, the pen is having low power. This is strange. Okay, so I would like to explain now what it means to have, or that this is P reducible. If we have a problem y, we reduce it into a problem x. For example, traveling salesperson problem to some scheduling problem. And then we get a solution for the scheduling problem and somehow can transform that into a solution of the traveling salesperson problem. And these two transformations, f and g here, have to be computable in polynomial time. Then the difficulty of solving problem y is only by polynomial expression different from the difficulty of solving problem x. And it means I can reduce, or this is polynomial time reducible to the problem x. And now we say that, as I said here, it is NP-hard, this problem x, if we actually can map every, or can reduce every problem out of NP onto this problem x. The first problem that was, for which that was chosen was the satisfiability problem, which is actually quite obvious. It tells that you are able to express every optimization problem here in NP as some kind of logic expression. And now you have to check the satisfiability of that logic expression, whether it is true or not for some assignment of the variables. And if the assignment of those variables makes that expression true, then you have a solution for your original problem y. And so the satisfiability was the first one which was shown to be NP-hard. And now the satisfiability problem itself is also in element, or it's also itself in NP. And all those problems which are NP-hard and which are themselves in NP are called NP-complete. And those obviously are the hardest problems in NP because they are as hard as all the other problems in NP. This is shown by this reducibility, and they themselves are also in NP. Now, if you have an NP-complete problem, you know this is a difficult problem. And so examples are the satisfiability problem, traveling salesperson problem, the click problem, whether you have a subset of a graph where all the elements are completely connected, or scheduling problems, and so on. So I have to get my pen reloaded here. This is supposed to be done in a very short time. Okay, so this is now what I wanted to briefly tell you about informatics background. We talked about optimization, and also this problem that we started from, this space filling problem, is also an NLP-complete problem. So this is a hard problem. Now you know what an NLP-complete problem is, at least very superficially, and you know how one could resolve or how one could try to solve those problems using a meta-heuristic like evolutionary algorithms. Okay. Now we get back to the optimization of load profiles. So we wanted to find out how we can actually fill that curve there. So we have here our degrees of freedom for the devices, and now we would like to get a solution. So this is one possible solution, and now this does not fit really very well. And so sometimes we can perform also local search. So we have a solution, and now we perform something which we call hill climbing. And hill climbing means we are at a certain situation and we assume that in the neighborhood there are better solutions, and we just try to go there by just locally modifying the solutions that we currently have. So local search in this case could be, well, we have the situation that you see there in the upper left, and now we just try to use an earlier starting time for that device. If we do that, now it fits. Just modify it slightly. Our algorithm has given us a solution which was not perfect, and we slightly modify a parameter and get a perfect fit. Or we could say, okay, this just below there, it was a starting time which was too early. We just have a later starting time. It fits. Or maybe there's a situation where we can say, okay, this device has a possibility to run slightly longer, and then we increase the runtime, and it fits. Or we can just switch it off a little bit earlier, and we decrease the runtime. Or you remember there were devices where we said they can run at certain range of voltages, different power. Maybe we can increase the power consumption, or we can decrease the power consumption. So these would be local search mechanisms where we modify a solution that we have obtained, try to use similar methods to try to get a better fit, to improve the solution. So this is the last part that we used in those optimization algorithms, local search, and then if it's still not good, we would continue with our evolutionary operators. If we are satisfied, that would be it. Okay. And then we get back to our device pool. Now we know how this algorithm is running. So now we shift the imbalances to some later point, and then we need possibilities to actually get for those later points also the appropriate power generation. So this is what we would like to get to respond to an imbalance that we have seen right now, where now is the first time unit. The problem is, I just told you we have to select all the information about the degrees of freedom of all the individual elements in the pool. We have to run the optimization algorithm, and we have to then tell them what to do. We have to make sure that the schedule is balanced again afterwards. This takes some time. And so it means that this would not be useful for having something like primary or secondary response to imbalances in the power schedule. So we would like to have a faster response. And I will come to that in a moment. First of all, as I see, I have here a few slides on what this optimization actually would do. So we have a simulation model where we have around 2,000 refrigerators and freezers in some pool. We have 84 combined heat and power plants. We run a simulation model for one day, 1,440 minutes. Average power consumption per hour is 56 kilowatt hours. Average power generation is 54 kilowatt hours, so it's not exactly in balance. And we run an optimization, an evolutionary algorithm using also local hertz, and use that on some device. So that was what we did there. And the reference is that the imbalance without coordination, if we have no coordination of the way these devices run, we have an imbalance of 11.2%. And if we have now coordination, if we can try to even out those imbalances, we can reduce the imbalance to 4.8%. And the difference between consumption and production was around 2%, so there is still some imbalance in there. But so the optimization actually provides a better result, can reduce the imbalance and the need for extra balancing power. Here is the simulation. So there's the device pool having a certain schedule, and now we assume we have an increased demand in the initial period. We have an increased supply there in the intermediate. Let me now try that pen again. We have there we have increased demand. Here we have increased supply, and there again we have increased. Aha! It has been recharged. So now we have this different schedule, and you see it's completely unbalanced here. There, compared to the initial schedule, now we have too much demand in this time period. Here we have too much supply, and there again we have too much demand. And now this has to be balanced by our pool, and so this has been simulated, and the result is that looking at different sizes of imbalances here, the actual and running that or having an imbalance for different time periods, like between 30 and 90 minutes, and having also different sizes of the imbalance, we get an improvement of the degree of imbalance that we have, like always shown with coordination and without coordination. So a reduction from here from 12% to 5.29%, or here down to 5.25%. Here, if we have, for example, 60 kilowatt imbalance for 90 minutes, would be 27% imbalance without coordination can be reduced to 17% with coordination. So it just shows this scheme obviously has some benefit. It can work. It's not working completely. So you cannot do too much. You have to comply with the restrictions of the devices. But nevertheless, you reduce the need for extra balancing power. So we can reduce the imbalances. There's no extra administration needed, because a device that is, or when you notice an imbalance, you can just do that completely inside the pool, get the information about the schedules, the degrees of freedom, let the evolutionary algorithm run, and get the new schedule. And so outside the pool, nobody needs to know the restrictions of the devices, and you can do that completely local to that pool. Certainly, we had quite a large pool. We had 1,900 fridges. So it was something like more than 1,000 households. But inside that pool, the information is known, but not outside. Disadvantages are that the imbalances still have to be optimized by the balancing group manager. So here, the balancing group manager would tell there is this imbalance. How can we modify that? He would get all the information, run the evolutionary algorithm, and then get the result. And also, what is not shown here or not listed here, the time requirements for optimization are or have to be taken into account. And so there's one more idea how we could actually work on that. And this idea has to do with using something which is called an elite group. It will show you what that is about. It will allow to balance small deviations immediately. It can find successors. It can be updated very easily. And it uses the pool for larger deviations. It has similar properties as primary and secondary control. You will see that on this slide. So what is the idea of an elite group? You select the best performing or the best performing elements, and the best performing means those elements which can respond the most, either positively or negatively, increasing the demand or decreasing the demand, or increasing the power generation, decreasing the power generation. So those elements are selected into an elite group, and then you have a deviation. Yeah, so here you have a deviation, and now this fridge here can satisfy that deviation, can just stop running. Now if it stopped running, it has to leave that pool. And it is replaced with a different device which now is more responsive, more capable to respond immediately. And then, certainly at some other time, this, or that here let me just see. Here you see there, there's too much power generation at that point in time. And so combined heat and power plant is ending its operation or reducing the power generation. And so maybe it can respond afterwards, but so there's even more need, as you can see here, more need for reducing power generation. So both can respond to that. And then there is some, what is this about? Aha. Here you see that the washing machine now is taking care of reducing the demand here, and then the next washing machine is responding, and this is not completely sufficient. One power generator here, the combined heat and power plant, is increasing its power generation, but it's not sufficient, and then the large imbalance is sent to the pool to take care of that. But what you have seen here is that in the elite group, the elements can respond directly to a deviation, at least to smaller deviations, and only what they cannot even out themselves has to be taken care of by the pool. And certainly if they stop running as members of the elite group, they lose their elite property, and they will have to run at a later time again. They will have to use that energy at some later time, so there are deviations at some later points in time which also have to be taken care of by the pool. And so this can be done by the pool because it's referring to later times, and so there's more time for optimizing. And so the elite group is responsible for short time deviations, which have to be there immediately, and those deviations at later times can be taken care of by the pool. And so this is primary control directly by the lead group, and secondary control later on by the pool based on the optimization algorithm. And in this way, we have a much better performance, and the elite group always consists of those elements of the pool which are the most responsive. And if one item or one device has responded, it may lose its property, may have to leave the elite group, and another device will enter. And certainly the capability of the elite group to respond immediately depends on the configuration of the pool. What kind of devices do you have there? To what extent will there always be a certain number of elements which can respond very fast? So this is something which is uncertainty, so a certain degree of uncertainty in there, but nevertheless you will always be able to have such an elite group. You can always take the best ones. The degree to which they can actually respond immediately depends on how well they actually are at the current point in time. So this is again here showing some animation of how they respond. So this is what's happening if you have the elite group. The balancing group manager now has to provide information about the size of the imbalance only. The elite group will respond immediately to that imbalance. It is, and then do something immediately, and then imbalances that are caused by that later on are taken care of by the pool. It is a completely self-organizing system. The optimization can be done by small computers, so these evolutionary algorithms that are necessary there can be run with very limited computational resources. There's not that much communication overhead. You have to collect information from the pool, and then you have to compute something and send out information again. You can have many different kinds of devices, and it is positive to have a heterogeneous pool, because then they can complement each other in the way they can respond to different requirements. You don't need extra hardware, assuming that you have intelligent devices that can communicate their preferences. You have your routing devices, your DSL routers in your house anyway, and so the idea behind this is we should get a solution which is actually not needing very expensive extra equipment, but which can use the equipment that is there to the best or in the best possible way. And so the major property is that it can respond quite fast by the elite group, and then have the subsequent response by the device pool, which is in some way similar to primary and secondary control on the higher level on the transmission grid. So that is, again, stated here, the advantages of the elite group. It is always the group of the most responsive elements of the device pool, and certainly the size of the elite group is a design parameter, depends on the size of the pool. Also that is a device parameter, or a design parameter. So let's say you have 100 elements or 500 or whatever is reasonable, this has to be tested out. And so elite group members respond immediately. The members who have responded may have to be replaced, which then are more responsive, and the balancing group manager or the demand side manager only has to specify the desired response. They don't have to worry about the way this imbalance is taken care of. This is done internally by the pool. And so the control or the intelligent decisions are taken inside the pool and don't have to be taken by the balancing group manager or the demand side manager. They just use the properties of the pool. They don't have to know the properties of the individual devices. This is the major advantage. So research questions are here definitely what the most appropriate configuration of such a pool is. How do you actually configure a pool in a larger area? How can you determine the guaranteed flexibility? What kind of statement can you make for a pool that you have about the guaranteed flexibility that it can offer? And what are the actual response times for a lead group and a pool? We have never run that in reality. We have simulated it in several scenarios, but we don't have real values for that. So this is something which is still something which can be done in research. And an idea is also not to have just one elite group, as we would see here. This would just be that these are pictures taken from the PhD thesis of Andreas Kamper. Here you might have just one elite group, or you might have several elite groups in your energy system. And they behave in a very flexible way, can offer flexibilities, and then by cooperating in a reasonable way, they can even out those imbalances and provide a stable system, improve the stability of the system. And so this is the major point. So we have some kind of controlled, self-organizing energy management. Controlled in a way means that we can ask them to do something, to provide a certain, like to provide more power or to reduce the power consumption, and they will do it locally. And there will also be ways to, if it's necessary, to control in devices directly, but the devices can perform this balancing in a widely self-organized way. This actually has been, like the idea of the elite group has been patented, so, but so far I don't know of any actual use of that patent. But it is a nice way of organizing the balancing task in the energy system in a self-organized, decentralized way, which so far is done in a centralized way on the transmission system level by those larger devices. Just a few diagrams in the end here on what kind of things can be achieved if you have that elite group. So this here is showing situation where you have a certain deviation, like you have your load curve, and here you have some very regular disturbance. This is a very regular disturbance. You have more power generation, less power generation, more power generation, just very regular. The question is whether your pool of devices can compensate that. And the red line here, around 0, it is almost exactly 0, shows that, like, the red line is the resulting power balance in that schedule, and it shows that there is no deviation in the end. So this imbalance, which is indicated in green here, can be completely compensated by the pool that was used there in this simulation. And here we have another situation where we don't have this very regular imbalance, that external imbalance, but something which looks more like the imbalances that we would have, for example, from wind power generation or from PV power generation. You have imbalances, and now you have to compensate for that. And you see that now it's not completely compensated. There are some parts here where you still have some imbalance, but it is significantly reduced by just rearranging the run times of the elements in this pool with an elite group. And here, this is shown again. This is exactly the same as up there. So this is just showing that it's not very much which is left here as imbalance. So this is obviously a scheme which has quite some potential for being used as a decentralized way of balancing out these disturbances in the energy system. The only problem is that you need some kind of incentive to let your devices take part in that, which is like a topic which is not addressed at all here, is the economic background. What is the business model behind that? How can you get an incentive for letting your devices participate in such an elite group and device pool and respond to those deviations? So it is technically possible, but now we need appropriate business models for that. And so far we have no business models for like economic incentives for actually offering such a capability. So in some way there must be a compensation scheme for compensating for this offering of flexibility. Okay, that is already the end of this chapter on self-organized balancing power. So I would say that it is a promising approach for reducing the need for balancing power, and we have seen that this is a source of extra cost in the energy system. If the day-ahead predictions are incorrect, and they are always incorrect to some extent, we always have some deviations during the day. We certainly have the intraday market to even that out, and then we have the balancing power, and the best thing certainly is to reduce the need for extra balancing power. And this can be done by such a decentralized scheme. And like the relevance of the practical application still has to be investigated, in particular the time constraints, how fast can we actually respond with such a scheme. And another issue is the derivation of guarantees for the duration of local balancing power. So what is actually the degree of service that we can provide with a specific device pool and elite group? This is something which also can be looked at. So many questions that can be investigated in more research. Okay, that is the end of this chapter. And then we actually can also start with our fourth chapter. So let's look at, hope you can still follow. It's a long time to have 3 hours of lectures, but I would like to just briefly start with that new chapter on energy management inside homes. So this is now, I just told you something which was energy management in some way across many homes. You have devices from many homes which cooperate in providing balancing power or control power. And now we look inside a house, and what we do now, what I show you now, has been designed, has been developed in the framework of certain funding programs, and I would like to tell you what these frameworks were about. So we had the e-energy program, where the target was to combine energy technology with market mechanisms in ICT. We had the economic incentive package, number 2, 7 years ago now, 2009 to 2011. That was the programs on ICT for electric mobility. We had model regions for electric mobility and also funding of research on electric storage. And so we had these 2 projects, Meregio and Meregio Mobile, plus that, like, this was extended by Chrome and iTsois, and now grid control. And in this chapter, which is quite a long chapter, I will show you more about what kind of local energy management systems have been designed within the framework of these projects. So what we are talking, or this framework that I just listed on the previous slide now is shown here in more, like with respect to the concrete projects. So we had down here in Baden-Württemberg, we had the program Meregio, moving to minimum emission regions. We had the MoMA problem that was at Mannheim. We had smart watts at Aachen. We had edema around Cologne. We had the regenerative model region Harz. So MoMA was model region Mannheim. We had e-intelligence around Oldenburg, northern Germany. And that was more or less the project, the model regions. And then we have had the electric mobility projects associated to that. And I think I've shown you this slide already, explaining our project Meregio, where we were participating with 5 chairs from different disciplines, from energy economics, informatics, telematics, management, and law. And we had 1,000 participants in that project. I have shown you just today these results from the test, how they respond to varying prices. And what we also designed here was a certificate which was supposed to show or to indicate best practice in some region, like a certificate that you have on an appliance having A, B, C levels of energy efficiency. The idea was to develop a certificate which could indicate the degree to which a certain region has very intelligent energy management. Okay, so what did we do in that project? Initially, we just looked at price elasticity. That's what I showed you in this one slide on the ability of the households to respond to different prices. Then we had a study on how the consumers actually could be controlled, how appliances could be controlled to respond to certain changes in the energy system. We did that with 840 participants. There were some participants getting local storage, like getting batteries in their houses, and in the end, the participants could take part in market situations. Actually, they got a certain game. There was actually something about, now people talk about gamification. We actually did that in that project. They could perform certain or make certain predictions about their energy consumption for the next day. And if you were very close, or the more accurate you was, or the more accurate you were, the better, or the more points you could get. And then these points could be exchanged into real money in the end. So this was trying to get the people aware of their energy consumption and making sure that they think about how they should use their devices in the next day, look at the price signals, and then end up in a better system. I've shown you that already. Like, this was the reference groups. This was the demand in the Meregio test region, and in the reference, completely the same over the days. This is over 1 week, and then after a few months, those two groups, the Meregio test group and the reference group, were compared with respect to their demand, and you see some deviations compared to the situation that was there before. And this is shown here in this diagram. You've seen the other diagram with the changes where power was increased in green time periods and decreased in red time periods. So this is just like, this was compared to 3 different price levels. And the interesting point was that in effect of having information on the current power consumption, the participants actually reduced their power consumption. Just by getting aware of how much power they were using, they reduced their power consumption. This was an effect which was not sustainable, like it would last for some time, but people always lose their interest after some time to look into those devices, and so this was not a continuing effect, but there was still some power reduction or so increased energy efficiency. And I have shown you this diagram already. And then we had this project Meregio Mobile, where we added electric mobility. So there the idea was how to integrate electric vehicles into a smart home environment. And in order to be able to demonstrate that, we were building our energy smart home lab, which is still sitting here on our campus and developed into one of our strategic infrastructures for performing research in new energy systems. And here actually we were active with 11 chairs, some more from informatics, some from electrical engineering, and so from 5 it was increased to 11 chairs. And we had new partners, we had Daimler, Opel, Stadtwerke, Bosch, SAP was there in Meregio also. Okay. So I said that here the idea was to have ICT for electric mobility. So the question is, what about electric mobility at all? You know that we have this national development plan to get 1 million electric vehicles by 2020. We now have the very recent incentive program. Let's see how that develops. We are far behind the initial assumptions. So the initial phase was the runtime of Meregio Mobile, market technology preparation. Now we are just at the end of the market development, and now we hope that the final 4 years here are the volume market, where we actually get the 1 million electric vehicles. And in 2030, the assumption is that we will get something like 6 million electric vehicles. So this development towards, or this transition in the way we use vehicles, like from internal combustion engines to electric engines, this will happen. There's no way that this will be stopped, but it takes some time. And what we need certainly is better battery technology, and we need charging infrastructure. This has not been developed as much as we had anticipated. And we need better electric vehicles. We have a few, but by far not sufficient. In particular in Germany, we have very few electric vehicles so far which are produced by German car manufacturers. They are promising to provide more, but it takes some time. We also have the plug-in electric vehicles, and so all this has to be developed. And what we can do with electric vehicles, we will look at next time we meet. Next time we meet will be 2 weeks from now, beginning of June, because next week there is Fronleichnam, a public holiday, and the week after that we will meet again. Okay, thank you for your attention. Das gibt's doch nicht.